Thank you, Professor Mario, for this kind introduction. My presentation for today deals with the current limitation and transient stability of grid-forming inverters. In this work, two well-known methods for current limitation are presented and compared. Then their impact on the transient stability is highlighted. Based on this comparative approach, a hybridization between both methods allows benefiting their advantage at once. The developed theoretical approach here will be validated through time domain simulation and experimentation also. Let's start first with a brief recall of the main features proved by grid-forming control, which is actually a promising capability that allows a voltage source converter to operate with a high potential compared to what has been achieved with a conventional grid following control. So in addition to their capability to inject a set bound of active and reactive power, grid-forming converters allows also an inherent inertial emulation, a high penetration rate of power converters in power system, and moreover, the knowledge of the grid phase and the frequency is not compulsory for synchronization, and thereby all the issues which has been linked to the grid following for synchronization are avoided. We can also mention their black step capability and their robustness against short circuit tissue and so on. However, many challenges are still under studies for such converters, such as their capability or their ability to overcome the high current in case of fault. Actually, since grid-forming converters are operating as a voltage source, they are very sensitive to the grid disturbances. So overcurrent can be caused by several factors, such as heavy load connection, line tripping, faults. But let's first recall the principle of synchronous machine. In fact, synchronous machine can handle 7 times its rated current during the fault. We can do the same thing with power converter, but it needs a huge oversizing to achieve such capability of synchronous generator, which results in higher cost and weight, and which is not benefit. While thanks to the flexibility of the control of voltage source converter, this task can be only handled through the control, and this is the main idea of this presentation. One of the most grid-forming control structures used is based on the cascaded control structure. The advantage of using such structure, in fact, is its simplicity of tuning and its implementation. And it is also able to generate a current reference in the inner control loop in order to protect the converter against overcurrent. In this presentation, we are taking the outer control, we are taking the droop control plus the transient virtual resistor as the outer control. And here the droop control consists of the droop gain and the low pass filter. In this presentation and in this work, in fact, the low pass filter cutoff frequency is taken very high in order to neglect the inertial effect, and the reactive droop control as well is neglected in order to keep the voltage across the capacitor close to the voltage reference. So to protect power converter against overcurrent, the first method consists to saturate the current reference of the inner current loop. So the converter moves from voltage regulation mode to the current regulation mode. There is a different way to do that in the literature. So some researchers are giving priority to D axis or Q axis during the fault, and other researchers does not care about the phase of the current. They are just limiting the magnitude of the current. So the implementation of the current saturation algorithm it's very easy. It is implemented between the current loop and voltage loop. And in this case, in order to avoid the wind up of the voltage controller during the saturation, an anti-wind up is required. In our case, we are just taking a simple algorithm to do that by freezing, in fact, the integrator gain of the voltage control when the current exceeds its maximum magnitude. Here it's defined as 20% more than the nominal current. The second method is so-called the virtual impedance for current limitation, and it is also called as a threshold virtual impedance. This method aims to modify the AC voltage magnitude when the current exceeds its nominal value to keep the current at a certain limit. This virtual impedance, in fact, is calculated through two parameters, which is kPRV and sigma x divided by R. Those values are determined under the worst case, which is the three-phase bolted fault at PCC level. The parameter here, sigma x divided by R, is usually chosen between 5 and 10, let's say that, in order to keep the total output impedance of the converter X higher always than R, and then to keep the PF characteristic of the droop control. In this presentation, we will take this sigma X divided by R equal to 5. The implementation of this control is illustrated by the following figure, where the voltage generated by the VI are subtracted from the voltage set point. To show the main differences between both methods, a response to a three-phase bolted fault of 150 milliseconds at PCC is assessed. We take an initial operating point of 0.8 at the beginning. So the results show that, in fact, both methods allow limiting the current in a good manner in the steady states. However, in the transient, there is a big difference between both methods, where with the virtual impedance, we can see a repetitive transient that may achieve 1.63 per unit during the first 25 milliseconds. This behavior can be simply explained by the indirect action of the VI on the current, since it depends mainly on the dynamic of the voltage controller. Means that during the fault, we are changing the reference of the voltage, but we need to wait for the dynamic of the controller to do that. And even if some authors, they propose a direct action on the modulated voltage, means that in that case, the system is controlled as an open loop, and then we let the system, behaving based on its output impedance and so on. And also in this case, we may have many oscillations. Compared to the VI, CSI has a better ability to limit the current in the first instance and also in the steady state, because it has a direct action, in fact, on the current reference. And with a good tuning of the current loop, we can have something like first order response in the current. So the first conclusion here is to say that the CSI is better than VI in terms of current limitation. This is the first thing. So once the fault is clear, of course, the power converter has to recover its equilibrium point or new equilibrium point in a stable manner. So in this slide, we'll study the impact of each current limitation method on the post-fault synchronization. To do that, let's first consider some assumptions. Here we neglect the inertia effect brought by the low-pass filter, and we assume that we neglect, in fact, the inner control and AC filter dynamics, assuming a sufficient decoupling between the inner and outer loops. And based on that, all the system will be modeled by the simple equation of the active power, where the angle is driven by the droop control. So here I didn't consider at the beginning the current limitation control, and I want just to explain the synchronism process of the grid-forming control based on the droop control, the grid-forming based on the droop control. So when the fault occurs, the active power droop to 0, resulting in a positive deviation and thus a positive angle deviation. And once the fault is clear here, the active power moves to a new operating point where pre-measurement is higher than P start. And therefore, the frequency omega m will be lower than omega g, which results in a negative deviation, of course, of the angle toward its equilibrium point. We defined a stable system if and only if delta C is equal or lower than delta max, and this angle is defined as the critical clearing angle. If the inertial effect is considered, of course, we will have an acceleration after fault clearing, means that delta CC, or the critical clearing angle, will be lower than delta max, which is not the case in this paper. Now, let's introduce the virtual impedance for current limitation. By doing this, the overall system can be presented as follows. From this figure, the active power formula is deduced. In this formula, the resistive part is considered to have more accurate results. And based on this formula, of course, the P delta curve is modified, and also the post-fault synchronization sequences are modified as well. So actually, when the fault is cleared, when the virtual impedance is implemented, the active power reach the operating point C, which is located in pre-measurement 2. At this specific point, the current is limited to its maximum value that determines LVI max and XVI max. Then the operating point moves from C to D. In fact, in this phase, the virtual impedance starts to decrease progressively, and at the operating point D, the VI is disabled completely, and the system can then recover to its equilibrium point through the previous equation of the active power. With the implementation of the virtual impedance, the critical clearing angle is not defined by delta max anymore, but it's defined by delta max VI. Doing the same things with the CSI, the overall system can be illustrated by the following scheme, and the active power exchange can be determined by pre-measurement 3 in this case. In fact, this equation, it's assumed that the current priority is given to the d-axis. I took this example from the literature, and all the results that I present here are based on this assumption. If the priority is not given to the d-axis, of course we will have delta plus the phase shift between the current and voltage. So by doing this, the phase sequence, the synchronization sequence will be changed once again. When the fault here is clear, the active power reach the operating C, then of course here the pre-measurement is higher than Pref, then the angle will decrease until the operating point D. So at this specific point, the nominal voltage will reach its nominal value, and then it's allow the system to go from the unsaturated mode, the saturated mode to the unsaturated mode, and then the system will recover stably to its operating point through the equation, the previous equation of the active power, which is Vm VE divided by X sinus delta. So considering the CSI, of course, the critical clearing angle in this case is delta max sat. Comparing both methods graphically, the critical clearing angle for the VI is higher than the CSI, and based on that, we can calculate the critical clearing time of each method, and the result shows clearly that the VI can maintain the stability for high fault duration. I took this example for the operating point 0.8, where the VI can keep 166 milliseconds, while the CSI can keep only 63 milliseconds for stability. To validate the proposed theoretical approach, time domain simulation here are performed, and from where it can be noticed for VI that the theoretical curves match the dynamic curves obtained from time domain simulation. We took two fault duration here, one fault duration lower than TCVI, and the second one is higher than TCVI. And in the first case, we see that we recover stability at the operating bound, and in the second case, the angle diverge, and then we lose the synchronism. Similarly to the VI, we did the same things for the current saturation algorithm, and once again, the sequences of synchronization are confirmed for both fault durations. To show the dynamic behavior of the current during the post-fault synchronization for each method, the first case here considered a fault duration of 63 milliseconds, which is close to TC saturation, to TC CSI. And the first result here showed that both methods, in fact, recovers their operating bound after fault clearing. And when the fault duration is a bit higher, then the system lead to instability with the CSI, while with the VI, the system keeps stable. So from this simulation results, the second conclusion is that the VI can keep the synchronism for high fault duration compared to the CSI. So let's recall the main conclusion till now. So we say that the CSI is better than VI in terms of current limitation, and the VI is better than CSI in terms of transient stability. So the aim of this slide is it consists to show that by hybridizing both methods here, we can benefit the advantage of CSI and the VI at once. In order to avoid simultaneous operation between both methods, so the level of limitation of CSI should be higher a little bit than the one of the VI. So we took, for example, E max SAT here for 125 and one max VI for 1.2. In that case, if there is a fault, all the transient will be limited by CSI, and the VI will play at the beginning the role of the anti-windup. So it decreases the level of the current after the first transient, and all the current limitation will be ensured by the VI and the post-fault synchronization as well. To demonstrate that, the same simulation made before is done for the hybrid current limitation control, where you can see clearly the sequences of the current limitation. You can see here at the beginning, at the first 10 milliseconds, the current limitation was guaranteed by the CSI. Then the current was decreased through the VI, and the rest of fault duration is guaranteed by the VI. And after fault clearing, you can see that the hybrid current limitation has the same dynamic as the VI, since in fact it's the VI which guarantee the post-fault synchronism.
1 minute, please.
Okay. Then when the fault duration is higher a little bit, then you can see that the hybrid current limitation have the same dynamic behavior as the VI. To confirm all the results obtained, we validate our proposed control theory by experimental bench, which has been, I will skip that. And you can see here that for an operating bound on 0.7, you can see that the system is keeping stable, and the dynamic behavior seen before is the same like the one that we got here in experimentation. So I will skip a little bit all the conclusion, because the main conclusion was that CSI is better, as I said before, but the hybridization of both methods can combine the advantage of each current limitation at once. However, despite the transient stability with VI is better than CSI, if the fault duration is higher than what we determined, then the risk of instability remains likely. So the disbound should be improved, and then all the theoretical approach applied here should be extended to unbalanced fault, and trying to fulfill, in fact, the requirement discussed in the last technical report of the INSOI. So Thank you for your attention, and feel free if you have any question.
Thank you, Gustavo. So the floor is now open for the question. So you can either raise your hand or using the Q&A panel or the chat, please. So it seems that there are no questions at the moment. Perhaps I can ask you a question.
Okay.
Taoufik, it's just a clarification and then eventually a question. So in your system, in your study, it seems that you model the external system by means of a Thevenin equivalent. Is that correct?
Yes, right.
So have you modeled also the inertial response of the external grid?
No, we didn't, but in this, of course, in this paper we didn't, but we applied this method in a 3-bus system where the frequency, of course, is variable. Yeah. And we consider also the inertial effect of some of those converters. And it seems that the proposed method, it works well.
So essentially, your conclusions are confirmed also with systems when you are connecting your converter to a system with a finite inertial response, right?
Yes, right.
Okay. So there is a question from Sébastien Michel. So I'm reading it. Maximum fault clearing times are very well understood for synchronous machines. What are the underlying limitations on the grid-forming converters that impose a limit on clearing time? Is it also sensitive to fault residual voltage? Taoufik.
Could you please repeat this question? I can stop this to see the question clearly. Okay.
Yeah, maximum fault clearing times are very well understood for synchronous machines. What are the underlying limitations on the grid forming converters that impose a limit on clearing times?
I think the voltage regulation, the inner voltage regulation can also it needs to be taken into account, because with synchronous machine, the regulation of the voltage is different from what we are doing here with the grid forming control. So if there is, for example, an electric turn with the grid forming converters, then the voltage will oscillate a lot, and the stability may not be linked also to the angle. It can be also linked to the voltage.